All right, welcome everyone. I'm Norman Wildberger. We're here at the University of New South Wales, and we're continuing with our course, our beginner's course on algebraic topology. This lecture, we're going to talk about covering spaces. So we've been talking about the fundamental group of a surface, and the covering spaces is naturally sort of associated with that topic, and there's an intimate connection between these covering spaces and fundamental groups. But before I talk about that, I want to talk a little bit about homomorphisms of fundamental groups. So suppose that we have X and Y topological spaces. And suppose that we have a function from one to the other. So f from x to y, a continuous function. Then associated to such a continuous function is an algebraic analog. So associated to this is a map, usually denoted F star, from the fundamental group of X to the fundamental group of Y. So let me describe this. Here's our space X. And usually when we talk about the fundamental group, we talk about a fixed point. So let's suppose that we have a fixed point x0 here. And over here is another space Y, perhaps like this, and some fixed point y0 and y. And let's suppose that we have a function f, or a map from x to y, which is continuous, and that also has the property that it sends x0 to y0. So it sends one base point to the other. All right, then how are we going to construct a map from the fundamental group at x to the fundamental group at y? Well, let me remind you that the objects of the fundamental group are loops based, say, at x0. And what a loop is really a map from the interval 0, 1 into the space, say alpha. And we can picture it, for example, like this. Okay, so here is the loop alpha, which is really a function from the interval into x. All right, so how are we going to use this setup to get a loop in the space y? Well, we're just going to compose these maps. We're going to start with the interval, apply the loop alpha to get a curve here, and then apply f to that to get the image. So we might call this f of alpha. So the rule is that f star of, maybe I'll just write the class of alpha. F star of alpha is by definition the class of the composite map where we apply alpha and then f. Maybe if we write composites like this, we'd write it like that. So that's taking loops in x to loops in y. Okay, this is a well-defined map. It turns out if you have a homotopy of loops, so if we change alpha to some neighboring alpha prime smoothly, continuously, then we can just transfer that homotopy to a homotopy over here to the corresponding image under F. So this is well defined. It's also a homomorphism. Since if we look at what it does to the multiplication of two paths, f star of alpha beta, well, then that's what you get. Then you get f star of alpha times f star of beta. So we do alpha first and then beta over here and then take the image. Well, then we're going to get the image of f of alpha under f followed by the image of beta. So this homomorphism of fundamental groups has a few important properties. We'll just list two of them. So suppose that we have a composite of maps, say a map F from x to y, sending x0 to y0, and then another continuous map, say G, to a space Z with a point Z0. Well, in that case, we get induced maps. So from pi of x, x0, we get a map to pi of y, y0, we're calling that f star. And then from pi of y, y0, we get a map from pi to pi of z, z0, that's g star. And then the proposition is that this is the same as taking the composite map, F circle G, and taking its induced map. And the second property is that, well, if you have the identity map, x, x0 goes to x, x0, the identity map, the function that doesn't change any point, that sends every point to itself, then the induced map I star from pi x, x0 to pi x, x0 is the identity homomorphism. And that's pretty well obvious. All right, so two basic properties of this association of homomorphism of fundamental groups to a function between topological spaces, or a mapping between topological spaces. All right, so now let's introduce the idea of a covering space. Okay, what a covering space is a pair of spaces, topological spaces, that are in a certain relation to each other. And usually the notation is something like this. We have a map P, say from a space X to a space B. And this space is called the base space. And the space is called covering space. And this map is called the covering map, or sometimes just projection. And the picture that associates, that we're going to draw for this kind of thing, is having some space. And you put the base here, and sort of think of that in some kind of plane, and then above it is some more complicated space, perhaps, space X. And we're thinking of the map as being some kind of projection from the top onto this base. So we have a rough picture like this for a covering space. Now, I haven't told you what a covering space is yet. Let me give a concrete example, and then we'll say what exactly makes a situation like this a covering space situation. So there's a main example that's kind of key in this subject, which is the map from the line to the circle. And the associated picture to it is to have the circle here sort of as the base, And then to have the line, well, visualized as this helix kind of thing, going up in that direction, and down here similarly. So here's the line, there's the circle, and we're imagining this projection is just sort of the vertical projection that sends every point, say x in here, directly to the point below it, p of x down here. Arithmetically, we can define this a little bit more precisely in the following way. So we'll think of A as being just our standard line, which for me usually means just the rational numbers. And for this purpose, we'll think of the circle as being the interval 0, 1 with the 0 point and the 1 point identified. So the circle is 0, 1 with 0 equals 1. So we're identifying these 2 points. Then what is the map that relates the covering space to the base space? What is the projection P? Well, the map is, we take a point x here, and we define P of x to be x mod 1. So for example, P of 3.2 would be 0.2. Or P of 7/5 would be 2/5. And P of minus 3 1/3 would be same as minus 1/3, which is 2/3. Now there's another way of thinking about this map which is useful. Uses a little bit of group theory, of abelian group theory. It's another interpretation, a little bit more sophisticated. So if we think of our line as being the rational numbers as an additive group, or as an abelian additive group, then we can think of the subgroup Z. The subgroup Z just consists of the integral points. Maybe we'll denote it like this. So there is the subgroup Z. Z is a subgroup of Q. Now, whenever we have an abelian group with a subgroup, one thing that we can think about is what's the quotient group. So the quotient group, Q mod Z, is the space of cosets of the subgroup. So it's consisting of cosets of Z in Q. And what do those cosets look like? Well, they just look like translates of Z. So they're things of the form A plus Z, where A is in Q. So for example, if we take an element, say 2/3, right there, then its coset consists of itself plus what you get when you add 1, what you get when you add 2, or subtract 1, or subtract 2. So we get equally spaced points like this. So in that blue, that's the coset 2/3 plus z. And now the space of all cosets is really the circle. So Q over Z is really the same as the circle, because the cosets themselves are parametrized by elements belonging to just this particular interval, 0, 1. Every coset has exactly one element in it in the interval 0, 1, as long as we make this identification that 0 is actually equal to 1, because it in fact belongs to the same original subgroup Z. So if we think of Z as being 0, 1, S1 as being 0, 1, with this identification 0 equals 1, then this is naturally associated to the cosets of Q in Z. Now with that set up, we can describe this covering map in a nice algebraic way. So then the covering map or projection P from the big space Q to the base space Q mod Z is, what are we doing when we do this projection? We're taking an element A and associating it to it the coset in which it lives. P of A is A plus Z. That's the coset which contains A. So that's a map from elements of Q to cosets of Z. And if you think about it, this is just the same as the mod 1 map, because, for example, if we take A is equal to 1.5, then the coset that it contains is the same as the coset containing a half. So for example, P of 3/2 will be the coset 3/2 plus Z, but that's the same as the coset 1/2 plus Z. So what we're really doing is we're really reducing the number mod 1. In other words, removing an integer part. The advantage in thinking about it this way is that this is a rather general situation where we map from a space to a quotient of the space. That's a typical kind of covering situation. All right, so now it's time to tell you what exactly a covering space is. What is it about this map that makes it a covering map and not just any old map? So the interesting property that this function has is the following. That if we take any point in the base, say x, and we look at the inverse image of x, all right, so we look at P inverse of x. That's all the things up here that get sent to x. Well, in that case, that's going to look like what? So we're just looking at all the things in the helix which are directly above this particular x. So there's one right here, another one right here, another one right here, another one right here. So there's sort of a discrete number of elements in the inverse image. So that's the first property, that P inverse of x is a discrete union. But there's something a little bit more important, more in addition, that the covering property has, namely that we can find a little open interval around x in the base. We can find a little interval, let's call it u. So that when we look at the inverse image of that u, we get a whole bunch of little pieces of the covering space, each of which is exactly a copy of U. So if U is a neighborhood of X, then P inverse of U is a disjoint union of pieces, each of which is exactly homeomorphic to U. A disjoint union of pieces, each homeomorphic to U via P. So these are the two properties that define a covering map. So let me say it sort of officially. Definition: if we have P from a space X to a space B, this is a covering map if, first of all, for any, say, maybe I'll use B in B. For any B in the base, P inverse of B is a disjoint union of points. And secondly, there is a neighborhood say U of B in B such that if we look at the inverse image of that neighborhood, P inverse of U, which is actually sitting in the big space, so that this thing here is actually a disjoint union of, well, small spaces, each homeomorphic to U under P. So in other words, if we look at the inverse image of any one of these pieces, say this one here, this is one element of, let's call it V. This is sitting inside P inverse of U. Then under P, under this projection, is exactly homeomorphic to the original neighborhood U downstairs. So each, we have all these individual little pieces sitting above the neighborhood. Each is exactly looking like the neighborhood. So what it means somehow conceptually is that as far as local considerations are concerned, the space X looks locally just like the space B. Any point in X, if you look at where it's sent to downstairs, it's the neighborhood around this point X looks just like the neighborhood of the base space near the image. So locally, you cannot tell the covering spaces apart. But globally, they can look quite different. All right, so let's have a look at some more examples of covering spaces. So example 2, let's look at P from the 2-sphere to the projective plane. This is the sphere, the projective plane. And the picture is this. So here's our sphere, S2. And how are we going to visualize the projective plane? Well, it's very closely connected to the sphere, of course. So the projective plane can be thought of as pairs of antipodal points on the sphere. Okay? So given any line through the origin, it meets the sphere in two antipodal points, say A and A bar. Okay? And the elements of P2, the elements of the projective plane, are just these pairs of antipodal points. Now, to make that a little bit easier to visualize, what we did before is we said, well, we can just look at the upper hemisphere. Any antipodal point pair has one element at least in the, say, northern hemisphere. So we can think of P2 as just being the northern hemisphere, as long as we make sure that we still identify antipodal points along the equator. Right. So if we have a point B on the equator and a point B bar, its antipodal point, sort of across the equator there, then we have to make sure to glue those two together. All right, so we got the sphere, and we have the projective plane. How are we going to define a covering map? We need to define a map P that takes a point in S2 and gives us a point in P2. So P from S2 to P2 is defined by, so if we take P of A is a point in the sphere, we're going to send that. The image is going to be the pair of points, A and A bar. The pair of points, A and its antipodal point, A bar. In other words, we just associate to a point in the sphere the line in which it's contained, or the one-dimensional subspace in which it's contained. That's another way of thinking about it. Or we can think of P of A is the one-dimensional subspace containing A. Now this is going to be a 2-to-1 map, because the image of A is going to be equal to the image of A bar. A bar is down here somewhere. P of A equals P of A bar. Both A and A bar get sent to the same pair of points in the projective plane. And what about the covering condition? Well, if we have any element in the projective plane, say this pair of antipodal points, and then a little neighborhood of it, we can think of it as just being a little neighborhood of that representative there, then its inverse image under the projection will consist of two little neighborhoods, one essentially the same one around A, and the other one essentially the same one around A bar. So if there is U, then P inverse of U consists of the union of these two little neighborhoods in the sphere, one around A and one around A bar. And each one of them individually looks exactly like the original neighborhood down here. So it's a covering map. For our third example, we'll go back to the situation that we started with a circle and the line, and in some sense look at a simpler variant, where we have the case where a circle is covering a circle. So let me illustrate this with this couple of circles. So here is a circle. Okay, we're going to think of this as the base circle that will be sitting on the table. And here's another circle. This circle is homeomorphic to that circle there. So let's consider a map between this circle and the base circle. There are many such maps. There are many continuous maps from this circle to this circle. One continuous map would be, for example, a constant map, where we send everything to just one point. That's not a covering map, because the inverse image would be the whole thing, not a discrete union of them. Another map would be the identity map, where we label the circle 0 to 1, and we label this circle 0 to 1, and we just associate to the point T here. That would be a 1-to-1 map. More interesting map, the covering map, is this one here, where we take this circle here, and I sort of fold it over like this. So I'm folding it twice like this, and then I'm going to project down onto the base circle. So what I'm really doing is I'm having a map that goes around the base circle twice and comes back to where it starts. Now if I look at any point in the base circle, say that one there, and look at its inverse image, well, the inverse image will consist of 2 points, namely the 2 points right here that are right above it. And if I look at any little neighborhood of that point in the circles, that little interval there, then the inverse image will be the union of the little interval around here and the little interval around there. So how can we visualize this? Well, let's do it this way. So here's the base circle, S1. And then the other one, the covering, I'll draw it like this. So going around once, going around twice. Okay, and this is sort of an obvious, every point lying above. We're thinking of this one sort of being in a horizontal plane, and this being in space above that horizontal plane. Well, how does this thing close? Well, this thing closes, I kind of have to go down. So we go around twice, and then we've got to close back up again. And now if I put this right on top of each other, it's a little bit hard, because this curve has to sort of self-intersect in order for it to lie exactly above the corresponding circle down here. So this is a 2-to-1 map. But of course we could also do variance. We could go 3-to-1. So we could put our base circle here, and we could go a covering map which goes around one more time, and then it comes back down. This would be a 3-to-1 covering. Now I'll leave it to you to think about an algebraic interpretation of this. So algebraically, we can visualize something like this as follows. We could think of it as being a map between Q and 2Z and Q of Z. So if we go back to the line Q and our integers, we said that the integers themselves form this subgroup. There. That was the integers. But we can consider another kind of subgroup too. We could consider, say, 2Z, which consists of this one and this one, this one, and so on. I'll draw it down here. So this is actually a smaller subgroup containing fewer elements. That's the subgroup 2Z. So what do the various quotients look like? Q over 2Z is the quotient of the line with respect to 2Z. Well, that looks like this. The representative examples would be this. So this is Q over 2Z. While Q over Z was the familiar interval that we started with. this one here. So that's Q over Z. And so what is the map? The map between this quotient and this quotient. The map is the map that sends A plus 2Z, a coset of the smaller group, to the coset of the bigger group, A plus Z. Which is also ultimately a mod 1 operation. So for example, if we take an element A here, then its projection will be here. Exactly 1 over, so we subtract 1 to get it in the interval associated to this one here. Now this kind of covering of a sort of a helix of a circle is a little bit problematic to draw because of that self-intersection of the helix. And there's an alternate way of thinking about it, which is kind of useful. So another physical model of that of, say, the helical covering of a circle uses a torus. And this model leads naturally to a very interesting subject called torus knots. So what's the idea there? Suppose we want to illustrate this, say, 3-to-1 mapping. Say the mapping, all right, so what we do is we go around. So this one's in front, and then this one's in front, and this one's in front, and then we have to go back there. There's a 3-to-1 map of the circle to the circle. So a way of visualizing this using a torus is the following. We consider a torus like this. And of course, a torus is a circle across a circle. We can think about 2 coordinates on the torus. If there's a base point, we can think of having one circle going, well, a bit more accurately, one circle going around like this, and then it will go around the back, come out front like this. It's one S1, sort of like the x-axis on the torus. And then there's the other circle going around like this, which is sort of like another S1, which is the y-axis. And so we can use these circles to coordinatize the torus. All right, so how can we make illustrate this 3-to-1 covering? Well, we can we can look at a loop on the torus that starts and ends here and goes once around this one and goes 3 times around this direction. So imagine a bug that's going around uniformly along this circle here, and at the same time it's going around this circle here, but it's going 3 times as fast around this circle as it's going around this circle. So by the time it goes once around this circle, it goes 3 times around this circle. Okay, so let's see if we can draw that. So it's going up like this, and it's there, and then it's going back, and then it's up again. Okay, and then now it's sort of back. It's gone 1 rotation around that circle, and now it's keeping on going. And then it comes at the back, and then it comes around the front. Oh, and then when it's around the back there, that's the second time. It's hitting our axis. And then it comes around here, and it's visible there. It comes back around here a third time. So 1, 2, 3 times. So if I'm thinking of this red curve now as the x space, that's a circle. And if I think of this base here as the base, say b equals s1, then I can define the map P from x to b by projection onto the y-axis. So P sends RS to, in these coordinates, well, we're just going to ignore the x coordinate and just send it to S. That's like projection onto the y-axis, if you like. Then this is a 3-to-1 map, because, for example, the inverse image of this point here on the base space is this one here, and this one here. While the image of this point here would be this one here, a little further on, maybe this one here, and then maybe a little further on this one here. So it's a 3-to-1 map. It's really topologically the same as this thing here, but in space we visualize it in such a way that the self-intersection has been eradicated by wrapping around the torus. All right, so once we start thinking about wrapping a circle around a torus, we encounter some interesting things. Why not think a little bit more generally? So if we wrap more generally around a torus, then we get so-called torus knots. And here's an example of a torus knot that I made this morning. All right, so what is this? Well, this is a circle, S1, which is wrapped around the torus. So let's just verify that. Let's say we'll start with this point right here, which you can't see very well. And with that point there, I can see it's right next to the valve here, okay? So all right, so if we keep going around, we go here. Let's see if I can put this somewhere so you can see it. All right, so we're starting here, slowly going around, and then we come out here, and then it goes around, and then it comes out here, and then over here, and then over here, and then over here, and then over here, and then through here, and back to where we started, I think. It's all one continuous curve, I can assure you. And you can kind of see that it wraps around the y-axis, or the circle that goes in this direction, 7 times, because you can sort of see 1, 2, 3, 4, 5, 6, 7 loops around. So it goes around 7 times this way when it makes one complete circuit. But it also goes 2 times around this way. Okay, when I was doing it, following it around, I actually went around this direction twice. So this is an example of a map from S1 to S1 cross S1, which algebraically we could describe in the following rather nice, simple way. We can define P of t to be, okay, we want this to go twice around the sort of the x direction. So I'll put 2t there. And we want to go 7 times around the y-axis direction. So I'll put a 7t there. And I'm doing all of that mod 1. T is in 0, 1. So this wraps twice along the x-axis. So in other words, it goes around in this direction twice. And 7 times along the y-axis. So that's the y-axis. It goes around 7 times around that direction. Now what's interesting about that is that if I was able to make the torus vanish, then I would just have a single loop in space. And then that loop would be a knot. It would be knotted. And the knot that we obtain is called a torus knot. So if we remove the torus, we get a loop in space, a torus knot. And let me try to show you what happens in a simpler case. So here is the somewhat simpler case when we have the map T goes to 2t, 3t mod 1. We go twice around the x-axis and 3 times around the y-axis. That can be visualized in a number of ways. Here's a diagrammatic way of representing it. So 0, 1, 2, 3, 1, 2, 3. I'm going to go around twice in one direction and 3 times in another direction. So I'm essentially taking a straight line path from 0, 0 to the point 2, 3. This is a planar picture where I'm working in the plane, and now I'm going to make the mod 1 version of this by blowing up a single square. So this is the picture of the torus that we usually have with these sides identified and these sides identified. So what's happened to the path is it started here and gone up to here, that's sort of stage 1. And then from here to here, that's stage 2. That's like that. It should be parallel. And then from here to here, stage 3. And finally stage 4, from here to here. So this is the same path on the torus where we've laid out the torus flat. In that case, it's just a straight line motion where we start here and we go up here, and once we get to here, well, then we're back to this point here. And then we go up here, and then that's the same as that point there. Keep going in this direction, that's the same as that point there. And finally we get to that point, which is the same point as we started. That point is the same as that point. And we've gone essentially 2 times in this direction and 3 times in this direction. And if I try to make a a diagram of it, we get something like this. There's our torus. These are the parts you can see on top of us. Wow. Okay, and these dotted lines are the things that behind that are not actually visible. Okay, and then if we remove the torus, then we would get so I'm hoping that if you look at this and you imagine removing the torus, you can see that the knot that we get is the trefoil knot. So the trefoil knot is what we get when we go around the torus 2 times in one direction and 3 times in another. So the problem is describe the torus knot associated to covering, or the map, S1 goes to S1 cross S1, T goes to 3T, 4T. Mod 1. So we go 3 times around the x-axis and 4 times around the y-axis.
What problem number is that?
That's a good question. What problem number? 3? I'm not entirely sure what problem number it is. 9?
So is that the first problem for this lecture?
The first problem of this lecture, yeah. All right, we'll take a break, and then we'll come back with a few more examples of covering spaces.